Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial System Engineering. This lecture is an ARMA modeling illustrated with a data example. In this lesson, I will introduce a data example, which is on modeling and prediction of the stock price for a large company, which have been around for many years. In this lesson, we'll focus on IBM, standing for International Business Machines. The company was initiated in 1911 as the Computing, Tabulating, Recording Company, which was a merger of 4 companies. Later, in 1933, it became IBM. Since the company has been around for more than 100 years, it has contributed to many innovations and it has experienced many disruptive events. For example, in 1964, IBM announced the first computer system family, a breakthrough at the time. In 1974, IBM developed the Universal Product Code, which changed the retail industry and other industry since it allows tracking trade items. In 1981, along with the World Bank, it developed financial swaps, a widely used financial product. In 1993, it experienced the highest loss in its history to date, a loss of $8 billion. In 2005, it sold its personal computing business and it was not sustainable. And in 2014, it sold its x86 server division. In 2015 and 2016, has started investing heavily in healthcare solutions and health analytics. What is a stock price? In financial terms, it is viewed as the perceived company's worth, since multiplied by number of shares gives the total company's worth. It is generally affected by a number of things, including volatility in the market, current economic conditions, popularity of the company, and events as the ones I mentioned in the previous slide. The analysis in this study is to develop a model to predict IBM's stock price, given that no major events are to be released. That is the usual business kind model. The model presented here is general and applies to the stock price of other companies, although its performance will be different. The data consists of daily stock price from January 22, 1960 until April 18, 2017. The daily stock price is available as open price, close price, and adjusted close, high and low price. We'll consider here adjusted close, which is the common price analyzed when daily stock price predictions are thought. Let's first visualize the time series for drawing insights on the model to be considered. We'll begin with reading the data file in R. The R command is read.table since the data file is an ASCII file. The input is the name of the file, ibmdaily.txt, and header equal to T, since the data columns have headers. Next, I use the asDate command in R to convert the dates provided in data into a date object in R. For this command, the input is a vector of dates converted into character with a specification on how the dates are recorded, for example, month, day, and year, in this order separated by /sign. It's important to get this correct, otherwise you will read the dates incorrectly. Then I add this column to the data matrix and use the attach command with the data matrix so that all columns in the data are read in R as individual vectors. Next, I define one of the events called Truven to be the date of acquisition of the Truven company in 2016. The other events are defined similarly. Then I use the ggplot command with input the date and the close price to plot the time series along with the vertical lines indicating the event acquisition of Truven in 2016 and also other events as will be provided in a plot. The vertical lines for all other events are added similarly as for Truven. I do not provide the entire R code here. You can find the complete R code in this lecture. Here is the ggplot of the daily stock price, specifically the adjusted close price along with the vertical lines indicating when all the events mentioned in the previous slide happened. There's several characteristics to point out. The trend is overall monotone, increasing with fluctuations in the later decades. There's no clear seasonality that can be evaluated visually. However, what is clear is the heteroscedasticity of the time series. The variability in the stock price clearly shows a big change from being significantly smaller in the early years versus much larger in later years. We also note that the events did not clearly trigger significant changes, at least as seen on the scale. For earlier events, it is hard to distinguish any differences because of the difference in scale. The price is slow with low volatility until around 1995, with more distinguishable changes thereafter. In fact, in order to better distinguish patterns throughout the entire time period, it is a good idea to use transformations that stabilize the variance and amplify local patterns such as the log transformation. Here I use this transformation on the adjusted close price, but everything else is the same as in the previous ggplot command, including the indication of the events with the vertical lines. This is a ggplot for the log transform stock price on the bottom. On the log scale, the patterns in the earlier years are much easier to distinguish. For example, we can see the increase in the stock price after the first family computer was launched in 1964. And we also see a significant drop in the price when the company had a very large loss in 1993. The merger and acquisition in 2015 and 2016 are followed by an increase in the stock price. Note that these observations on increases and decreases of the stock price associated with specific events are not necessarily caused by the events, but also can be triggered by other macroeconomic events or company performance. In both plots, the increasing trend is the most prevalent pattern. One way to remove a trend is to consider the difference process. Here I redefine the stock price as a time series with a frequency specifying that this is daily data starting with January 2nd, 1960. Then I use the difference R command to take the difference with the default of the first order difference. I also plotted the ACF and PACF to see whether another differencing of the data is needed and or whether the resulting process is stationary. Here are the ACF and the PACF, or the partial autocovariance function plots. Interestingly, the two plots look just like those for the white noise we simulated in the previous lesson. Do we still then need to apply an ARMA model to model the difference process, or is it enough to take the difference since the difference process seems to look like white noise? We'll address this question in this lesson and in the next lessons. Next, I applied the ARMA modeling. I used ARMA to take into account the trend through differencing. I assume only one order difference, and thus set the difference order fixed to equal to 1. Here, I only select the orders of the AR and MA polynomials. We obtain here the P and Q orders for the model with a minimum AIC value. For this, we need to fit the ARMA model for all combinations of R and MA orders up to a maximum order for both polynomials. Here I set the maximum order to be 5 and consider orders from 0 to 5 for both the AR and MA components. Note that I specify here n order equal to 6, but that means I consider the orders from 0 to 5 as specified in the definition of P and Q. I loop over all combinations of the orders and feed the ARMA model for all those combinations and save the AIC values in a matrix for all the combinations. The selected orders are P equal to 2 and Q equal to 0. Last, we fit the model for the selected orders, called here the final model. Here are the residual plots for the fitted ARMA model. The R code for obtaining these plots is provided in the complete R code for this data example available with this lecture. The residual plot does not show to have a pattern. The variance of the residuals is also constant. The ACF plot has only the first lag equal to 1, where all other values for the ACF, for the sample ACF, are small within the confidence band of the sample ACF. The same for the sample PACF. The values are all within the confidence band. The QQ normal plot shows both a left and a right tail, an indication that the residuals may have more of a t-distribution than a normal distribution, although otherwise quite symmetric. Last, we also apply the hypothesis testing procedures for independence or zero correlation using the box, Pierce, and Lewin box test. The R commands are on the slide. The R output of this implementation is here. The R output provides the test values along with the p-value of the test. Note that the null hypothesis in this test is that the time series process, here it is the residual process, consists of uncorrelated variables. Thus, this is one rare case when we want large p-values so that we do not reject the null hypothesis. The p-values for both tests are large, indicating that that is plausible for the residuals to be uncorrelated. In summary, in this lesson, I illustrated the model fitting of ARMA modeling with the data example. We're interested in the prediction and modeling the IBM stock price. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on illustration of ARMA models with a particular data example. In this lesson, I will focus on forecasting of the ARMA model for the IBM stock price. I'll remind you that this analysis in this study is to develop a model to predict IBM stock price. We'll only consider here adjusted close price, which is the common price analyzed when daily stock price prediction are thought. We'll first implement and evaluate a 10 days ahead prediction. For this, I set apart the last 10 days of the time series, then feed the model based on the time series discarding the last 10 days, and then predict the last days to compare with the observed values of the time series for these 10 days. The predict command in R takes as an input the ARMA object, along with the number of lags ahead for the prediction. The prediction provides the predicted time series values, along with pointwise confidence intervals for the prediction. Then we plot the time series data along with predicted values and the confidence band. We do not plot the entire history of the time series, but only the last 50 days of the time series. We overlay the predicted values in red along with the confidence band in blue. A few noteworthy points to make are as follows. First, the time series is recorded from the most recent days to the 1960s. Thus, I use the reverse command to reverse the time series. Second, for both the observed data and the predicted time series values, I transform back using the exponential function, since here we predicted the log of the stock price and not the stock price itself. Thus, for evaluating the predictions of the stock price, we need to transform back with the inverse of the log function, the exponential. The same exponential transformation is applied to the lower and the upper bounds. The corresponding plot is here. The black line is the observed time series. The red points are the predicted values along with the confidence bands in blue. All the observed values are within the confidence band. The predicted values are somewhere close to the observed values, except that they do not capture the decreasing trend which begins during this 10 days of forecasting. The confidence band is quite wide, indicating that there is large volatility or uncertainty in the prediction. But how good are these predictions? We can compare the predictions with the observed time series values. Note that in the real world, we do not have the observed time series in the future at the time of prediction, and thus we cannot evaluate the prediction accuracy of a model. In this case, however, we first pretend we do not have the observed time series for the last 10 days and predict the time series for these days to compare here with the observed time series. Generally, the question, how good is a prediction, comprises of two separate aspects. First, measuring the predictive accuracy per se. Second, comparing various forecasting models. Here we simply evaluate the predictive accuracy. The most common reported measures of predictive accuracy are mean square prediction error, abbreviated MSPE, or mean absolute prediction errors, abbreviated MAE, percentage measures such as the mean absolute percentage error, abbreviated MAPE, and precision error. The three measures can be computed, the four measures can be computed using the R as provided on the slide. MSPE is the sum of squared differences between predicted and observed. MAE is the sum of the absolute values of the differences. MAPE is the sum of the absolute values of the differences scaled by the observed responses. The precision error is the ratio between the mean square prediction error and the sum of the square differences between the responses and the mean of the responses. MSPE is appropriate for evaluating prediction accuracy of a model using the best linear prediction approach, but it depends on scales and it is sensitive to outliers. MAE is not appropriate to evaluate prediction accuracy of the best linear prediction, and it depends on scales, but it is robust to outliers. MAPE is not appropriate again to evaluate prediction accuracy of the best linear prediction, but it does not depend on a scale, and it is robust to outliers. PM, or the percentage measure, is appropriate for evaluating prediction accuracy of the best linear prediction, and it does not depend on the scale. The PM measure is reminiscent of the regression R-squared used in linear regression. It can be interpreted as the proportion between the variability in the prediction and the variability in the new data. While MAE and MAPE are commonly used to evaluate prediction accuracy, I recommend using the precision measure. Another approach, a fourth approach for evaluating a prediction, is by checking whether the observed values fall within the prediction intervals as provided in the last command. For this data example, the accuracy measures are provided in this R output. The precision measure is 5.38, which means that the proportion between the variability in the prediction and the variability in the new data is 5.38. That is, the variability in the prediction is significantly larger than the variability in the data. The closer this is to 0, the better the prediction is. However, the prediction measure is quite large, indicating poor performance in predicting the 10 days. Last, we also note that all observed responses fall within the prediction intervals. However, as I pointed out before, the prediction bands are quite large, indicating significant uncertainty in the predictions. Let's also consider prediction of the 10 days, but this time on a rolling basis. That is, for each day, we feed the model with the entire time series up to that day and predict only 1 day ahead. Apply this for each of the 10 days. To do this, I used a loop command for I from 1 to 10, where each I corresponds here to 1 day. We then save not only the prediction, but also the prediction intervals. Last, I plotted the predictions based on this approach along with the observations of the time series. The complete R code is not provided here on the slide, but it's available with this lecture. The plot here compares the predictions from this approach, where the predictions for each of the 10 days are provided on a rolling basis, to the predictions obtained from the previous approach, where the predictions for all 10 days are provided all at once. As expected, the predictions using the 1 day ahead, shown in green, are much closer to the observed time series than the predictions from the 10 days ahead approach, shown in red. Moreover, the confidence bands from the rolling basis predictions, shown in purple, are much tighter than for the 10 days ahead predictions. This is again expected since there is less uncertainty from 1 day to another as compared from 1 day and looking 10 days ahead. While the predictions using the one-day ahead approach on a rolling basis is preferable since the predictions are significantly better, we cannot always use such an approach since there are situations when we want to predict 10 days ahead in the future rather than one day ahead. Generally, different models may be used for different lags ahead predictions. Similar to the previous approach, we can also evaluate the accuracy of the prediction using accuracy measures. The R code is the same as before, except that it is now applied to the predictions based on the one day ahead rolling basis approach. The R output is here. I will focus here on the interpretation of the precision of the percentage measure, the PM measure. Compared to the 10 days ahead prediction, the PM measure is 0.4 as opposed to 5.38, which was the measure for the predictions with 10 days ahead. As mentioned previously, we seek a precision measure that is close to 0 as it is for this prediction. Last, I also note that the observed responses fall within the prediction intervals. The confidence intervals show also less uncertainty. In summary, in this lesson, I illustrated the data example on predicting the stock price for IBM. Thank you.